Hello, I'm Jim Salsbury with Mitutoyo America Corporation, and welcome to the Metrology Training Lab. In past episodes, we've defined the concept of calibration and also discussed the purpose of calibration. In this episode, we're going to talk about what makes a good calibration method. Calibration plays an important role in establishing traceability of measurements back to international definitions, like the meter or the inch. But when it comes to measuring instruments, like this micrometer, or this caliper, or this indicator, or these gauge blocks, calibration is really about a search for errors. We want to develop a calibration method that efficiently hunts down and finds any potential errors in the measuring instrument. A good calibration mitigates the risk of measuring instruments not performing as accurately as expected or required. But calibration takes time and costs money. And since different organizations have different thresholds of acceptable risk, there's really no perfect or best calibration method. A good calibration method will quickly search for errors and give a sufficient likelihood that the measuring equipment is either good or bad for its intended purpose. A good calibration method is a well-engineered test that finds the optimal balance between cost and risk. So what does a good calibration method look like? For this caliper, micrometer, indicator, gauge block, even this surface plate. We get these questions a lot here at the Metrology Training Lab, and we have students come here all the time to learn good methods. Now, I'm a big fan of not reinventing the wheel, and there are a lot of smart people have already thought about these calibration methods. In fact, there are American national standards that address the calibration of all these items. For not too much money, you can get some pretty awesome guidance documents in this area. We know that here at Mitutoyo America because we use these standards, and we also help contribute to developing them. In the United States, the American Society of Mechanical Engineers, or ASME, has the responsibility for developing American national standards in the dimensional measurement area. That work is managed by a committee called ASME B89, which is comprised of experts from a variety of organizations, including end users, equipment manufacturers, calibration providers, distributors, government agencies. In later episodes of the Metrology Training Lab, we will cover some calibration methods in detail. But let me give you some insights based on the appropriate ASME B89 standards. The following are often done wrong in calibration, but are covered quite nicely in the standards. For dial indicators, there is ASME B89.1.10. And one of the topics in that standard is about properly checking the hysteresis of the indication, which is the error that occurs when you approach the same position from different directions, as we just showed here at the 9 o'clock position. For gauge blocks, the ASME B89.1.9 standard discusses the importance of checking the variation in length by calibrating the gauge block at the gauge points and at all 4 corners. All 5 points must be in tolerance to state conformance to the grade. For outside micrometers, the ASME B89.1.13 standard recommends 5 specific size gauge blocks for calibration. And these gauge blocks are not commonly available sizes in a standard set of gauge blocks. The reason for these specific sizes is that they will force the micrometer thimble to be in different orientations for each test point. The goal is to have an efficient test that looks for errors across the measuring range simultaneously with errors within a rotation of the thimble. For calipers, the ASME B89.1.14 standard discusses the need to check the internal measuring jaws with a small ring gauge around 0.2 inches in diameter. This test is specifically designed to test for the additional air that can occur due to the crossed knife edge measuring faces. Lastly, on surface plates, the ASME B89.3.7 standard discusses the importance of the two different flatness specifications for surface plates. One being a local flatness, often called the repeat reading, and the other being the overall flatness, which covers a much larger area of the entire surface plate. A proper calibration needs to address both flatness specifications. Unfortunately, there is confusion in what makes a good calibration method. You really need to understand the technology inside the measuring equipment to develop the calibration method. Or you can take advantage of the appropriate documented standard, which has already done all that work for you. In future episodes of the Metrology Training Lab, we will go into more detail on the calibration of these specific measuring instruments. But for now, I hope you've gained some insight into what makes a good calibration method and the power of the available standards. Thank you. I'm Jim Salsbury, and I'll see you next time from the Metrology Training Lab.